Okay, we will do the Fano's inequality. We will use the Fano's inequality for backward proof of the channel coding theorem. So recall the Fano's inequality. Let E is equal to 1 when we made a mistake in deciding the transmitted index. So when W prime is not equal to W, E is equal to 1. When W prime is equal to W, E is equal to 0. So no error, error. So probability of error is, by definition, that is the PEN. And then probability of error is equal to 0. That means probability of no error. So it is 1 minus PE. So we can consider two different expansions of entropy of EW given Yn. So we can do it for first with the error random variable E, right? So this is HW given E, and doing it again with W. So HW plus HE given W. So we do these expansions twice. So this has to be equal to each other by the definition of entropy, okay? And then we note that the second item, which is this one, when the index, transmitted index and Yn is given, that means there is no error. So basically there is no uncertainty on the error random variable. So this part, the entropy is 0. So we have a equality that we can use, which is this part, since this is equal to 0. So that is going. That is the equality that we will use. Okay, for the Fano's inequality. Okay. Okay, so finally, the Fano's inequality for converse proof of the channel coding theorem, we will use this equality that we have derived in a little earlier. And note that this part is less than or equal to 1 because E is a random variable, E is a binary random variable. So the conditional entropy of E should be less than, should be upper bounded by 1, okay? And for this one, we have done the decomposition right here, as we have done in the past. So basically, we evaluate for E is equal to 0 first, and then when E is equal to 1 next, and then we need to combine the two. So basically, after you have done this, then we can take a look at the entropy of this item. The first item, that means given received the signal Yn or received the word Yn, and there is no error, then there is no uncertainty on the input index W. So the entropy of this part is 0. So the first term is 0. And there's a second term by the definition of random variable E. So probability E is equal to 1 is PE. And what about this part? And this part says error occurs. Error occurred. That means we need to exclude the transmitted index, and then the uncertainty is on the rest of the indices except the transmitted index. So, and since W is uniform random, Basically, that is log 2 of the size of the message set, which is excluding the transmitted index. The size of the message set is n-1. So we use this upper bound on excluding this -1, and we have this. So strictly, we could say this way, but m is very large, right? Because it's 2 to the power of nr. Compared to compared to 1, so taking 1 away doesn't make too much difference, so we can just say inequality as well. So PE n log 2 of 2nr, so we have nr appear right here. All right, so that's the second part. So this is PE nr. And finally, we have this one evaluated entropy of W given Yn, entropy of Xn given Yn. So basically, we draw this picture again, encoder, then we have Xn, send it over the channel, n times, you get Yn, decoder, we made a decision W prime. So remember this picture. That means if these two are 1-to-1, W and Xn, basically equality is achieved. And then we are using the 1-to-1 case. So this is equality. So that part is equal to Xn, Yn, and this part is upper bounded by 1. The first item is, and the second item is upper bounded by PE times NR. So HXN given YN is upper bounded by this. So we have that. So this is the Fano's inequality that we have considered in chapter 3. We have reviewed it right here. Okay, so we will use this upper bound in the proof. Okay, so next chart we have the proof. So this is exactly the same with the zero error code proof. Basically, we have any sequence of code with the maximal error approaching 0. Then basically the rate of such code must be less than or equal to C. So that's what we need to prove. And as we have done in the zero error code proof, so zero error code part, this part was 0, right? This part was 0, but this part, it is not going to be 0, but we'll use the Fano's inequality, and we'll have this term. That's the only difference. We'll have this term. Previously, this term was 0 in the case of zero error probability. And having this, and then we compare with this one and that, and the mutual information part using DMC and the capacity should be upper bounded by n times C. All right, so this is the part that is involved in the Fano's inequality. This is the part, it was 0, exactly 0 in the case of zero error code. But this is not exactly 0 in the case of any code, okay, with the maximal error approaching 0, okay. So once you have this and both sides, you divide by n. So this becomes 1 over n plus PE times R plus C. Okay, so this term is approaching 0, and the R is a fixed number. So this goes down to 0. So rate R should be, and this also goes down to 0. So rate R should be less than or equal to C as n goes to infinity. So that's the end of the proof uh, for the converse part of the channel coding theorem. Okay, I think that's it for this proof.